So your first question, on the ISS, a physics student measures the Earth's gravitational field to be 8.75 newtons per kilogram. How fast is the ISS moving? Well, the key is they've given you the gravitational field. What's the gravitational field strength? Well, the gravitational strength is given by little g, and to calculate it, it's big G, big M over r squared. It actually comes from, it can be derived from this, the fact that if we say gravity equals gravity, if we say mass times gravitational field, the mass in the gravitational field, little m, has to be big G, big M over r squared. Both equations for gravity have to work on the Earth. We find that the little m's cancel, and we get a universal expression for calculating the acceleration due to gravity or the gravitational field strength anywhere in space, on any planet. If you know the mass of the planet and how far you are from the center of the planet, that will tell you what g is. In fact, if you run these numbers for Earth, you'll get a lovely 9.8 right there. So the fact that they gave us this, and they told us that g was 8.75, well, that means I can solve for the radius. I can. It's going to be r squared equals big G, big M over 8.75. It's going to be, get rid of the squared, square root, where big G, 6.67 times 10 to the negative 11. Big M is where ISS is around the Earth, so it's going to be 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, all over 8.75. This must be happening at an orbital radius of square root of that there. Now that's the distance from the center of the Earth. 6.75. I'll carry some extra sig figs because this is not my final answer. I'll go 6.7516 times 10 to the 6th. How about 6.751600? Well, times 10 to the 6th. Meters. That's above the Earth, which is good, because the Earth's radius is 6.38 times 10 to the 6th. So, hey, we are in orbit. Now that I have the radius, it actually wants me to find how fast we're moving. I can get this probably in a couple of ways. Probably I can use the fact that, let's see. I would probably now say this 8.75 is also my circular acceleration. That gravitational field strength is that there. I think I can say that V equals the square root of R times A. If I take this number, times it by 8.75, and then we square root. Let's find out. Are we lucky? Hey, look at that. 7,690. 7,690. Now, why can I say that? Since gravity is what's pulling me in a circle, gravity is what's accelerating me in a circle, and gravitational field strength it is also an acceleration. Newtons per coulomb, or you can think of it as meters per second squared, so I can treat it like it's the circular acceleration. That's probably how I do that one. That's a fairly challenging question, by the way. Your second one. I haven't done this one, so I got to think about this. This is kind of cool. First of all, anytime I see a scale measures the normal force. So really, what I'm going to be finding in this question is the normal force. That will be the scale measurement. Well, at the bottom, what are the forces acting on this object? Get the obvious one. Gravity down. We're on the Earth, so I can use the mg version of gravity. It is moving in a circle, which means the net force has to be pointing towards the center, so there must be a bigger force, a winning force, pointing towards the center. You know what? That's the normal force. So, as an equation, I'm going to have normal force minus gravity equals ma c, because I'm moving in a circle. Which version of c am I going to use? I think I'm going to use the one with the v squared over r. So I'm going to get the normal force equals mg plus mv squared over r. Well, they gave me the radius. R is 0.156 meters. They gave me you know what they didn't give me? They didn't give me v. Or did they? You know what? The radius is also the height. The height is 0.156 meters. I think I see a curvy path. I see a change in height. I see a change in speed. I think I can pull out a little bit of conservation of energy. I think I can say at the top, KE initial plus PE initial equals KE final plus PE final. Where at the bottom of the bowl, that's 0. We're starting at rest. I think I can say MGH initial, where H initial is actually, woohoo, my radius, equals a half mv squared at the bottom. Conveniently, the masses cancel, and I was going to get the v by itself, but I notice I have a v squared here. I'm going to get the v squared by itself. I'm just going to say 2 times GR times GR equals squared, and I can stick that there. So now my equation is going to modify. The normal force is going to be mg plus m over r, where v squared is 2gr. Hey, you know, look at that. Even an r cancels. Who would have thunk? In fact, I think I'm going to get 1 mg plus 2 mg's. Oh, I love it when an equation comes together. I think I'm going to get 3 mg's. What was the mass? They told me 2.5. So if I go 3 times 2.5 times 9.8, I get 73.5. Is that what we, woohoo! Look at that. Magic, milk and honey. Oh, good stuff. So I get 3 times 2.5 times 9.8 equals 73.5 newtons. Hope that helps.